All right, so we're going to finish chapter 6 today, which is the last thing that will be on the exam, and then we will possibly start chapter 7, which is the next section, depending on how quickly we get through this. So one last reminder about the exam review, which is going to be Friday of this week. I believe that's the 22nd, and 1 p.m. in this room. Okay, so last reminder about that, which I encourage you to attend to help kickstart your exam preparation going into next week. And then, like I said, I still haven't gone through it yet and done it in detail, but I will have updated office hours for next week that I'll post on Blackboard and probably email you about, so you're aware of when I'm available next week during the exam. Okay, let's get into then the last major topic for this chapter, which is solution stoichiometry. So the book kind of covers this throughout the chapter as it introduces the different types of chemical equations, and I chose to just put it all to the end and kind of group it all together. So the idea here is it's not really any different than the stoichiometry we've been doing all through chapter 5. So if you're comfortable with a lot of that stuff with using moles and mole ratios and things, we're really just going to add one extra layer on top of that with what we're doing today. So if we remember from the chapter 5 when we learned the basics of stoichiometry is that moles are the key quantity. So everything involves converting to moles primarily as your first step when you're doing a stoichiometry problem. And as was made abundantly clear from all the examples we did and all the homework problems you had the last couple of weeks, it's because molar ratios, which come from balanced chemical equations, the coefficients in those equations, are what we use to convert an amount of one species, a reactant or a product, into an amount of another, which is a separate reactant or product in that same chemical reaction. So once you have moles of one substance, you can use mole ratios to convert to moles of another substance, and you're off to the races. So we're going to be doing the same thing here. That key step is still the same, but the difference is that before, the relationships that we had for moles were either mass, which uses molar mass, or in rarer cases we would use number of atoms and molecules and Avogadro's number to do that. What we're doing now in most cases with solution reactions is we're going to use volume and molarity. So we introduced molarity earlier on in this chapter as a relationship between moles and liters of solution. So as an example, we learned that we can use this capital M molarity as a conversion factor. So we want to know how many moles of sodium chloride are in 236 milliliters of a 0.524 molar solution. We remember that the definition of molarity with capital M is moles per liter of solution. So 0.524 molar means that we have 0.524 moles of our solute, which in this case is sodium chloride NaCl, per 1 liter of solution. And then a helpful shortcut that I will use a lot, so I don't want you to be confused when I start doing it, is to realize that 1 liter is equal to 1,000 milliliters. That we should know already too. And so we can rewrite this ratio also as 0.524 moles of NaCl per 1,000 milliliters of solution. And the reason why this is often helpful is because sort of the typical scale that we work on for chemical reactions in a laboratory setting is milliliters, not liters. So you're very often going to have problems where it says we have this many milliliters of solution and you have to use molarity as a conversion factor. And so you can use this sort of directly instead of having to go through the separate step of converting to milliliters first. It works either way, so mathematically they're equivalent, but this can save us at least one step in the process by using that as a sort of a combined ratio. All right, so then what we can figure out for this example here is if we want to find moles of sodium chloride in that solution, we start with the volume that we're given, which is 236 milliliters. So in the chapter 5 type of stoichiometry, usually mass was the first quantity we started with. Now we're starting with volume of a solution, and the conversion factor is going to be the molarity of that solution. So we use 0.524 moles of NaCl per 1,000 milliliters, if we want to use that shortcut directly, 1,000 milliliters of the solution. Milliliters cancel out, and that gets us into moles of our solute, which numerically in this case would be 0.124. So this step is what we're going to be using again and again in these solution stoichiometry problems. We're going to have a volume of a solution, we're going to have its molarity, and we're going to use the product of the two to determine how many moles of that solute we have, which is going to be participating in some sort of a chemical reaction like we've been learning about. So that's really the only additional step, and so that allows us to then update our stoichiometry flow chart. So we sort of introduced this in chapter 5, where we have, let's say, two different species A and B, which are involved in a chemical reaction. They can be either a reactant and a product, or two reactants, two products, really any combination of two species in a chemical reaction. And so what we saw was that in stoichiometry, the key conversion that we have to be able to do is take moles of one substance and convert into moles of another substance using the reaction coefficients from the balanced equation. So that is the step that is going to be really common for any type of stoichiometry problem. And then what we did in chapter 5 was we saw that we can convert into and out of moles by starting with, for example, the mass. So if we have the mass of a substance and its molar mass or molecular weight, we can convert between mass and moles, and that was a step that we used a lot in the previous chapter. And we can also do the same for the other species. Once we convert to moles of that species, we can use its molar mass to convert back into mass, or start with mass and convert into moles, either way. All right, so we had this was the typical framework that we operated in the previous stuff we were doing. We also saw at times, although it's not a very practical way, but it is something you can do on paper, is that we could convert into atoms or molecules of a species using Avogadro's number. So that's that 6.02 times 10 to the 23rd. So again, if we have a number of moles, we can convert in a number of atoms or molecules, depending if it's an element or a compound, or we can do vice versa. Same thing for the other substance B. We could sometimes see that with Avogadro's number there as well. So there's something else we saw occasionally, though not as common, is doing the mass to mole conversions. The other thing that maybe I should try to put on here if it doesn't get too sloppy is we can also relate these two directly with the reaction coefficients. All right, so there was a couple of problems on the homework like that caused a little bit of confusion, but remember that when we read a chemical equation that has coefficients in it, we can interpret those coefficients as either mole ratios, the number of moles of each substance that reacts and is formed, or we can interpret those as the individual number of atoms and molecules that react at a sort of microscopic level. So it works both ways, so you can also use the reaction coefficients directly to go between here and here, although like I said, going through moles is the more common way of doing it. And then the little variation that we're going to introduce today is to use molarity to convert between moles of substance and volume of an aqueous solution. Okay, so if we know the volume of the solution and we know the molarity, we can convert using that relationship. Same with the other substance B. If it's also an aqueous solution, we can use the volume of that aqueous solution and relate it to the number of moles using molarity. All right, and depending on the type of problem we're doing, we might go in both directions. We might convert from volume of solution into moles, or we might find the number of moles of substance and then use that to determine what the molarity or volume of that solution is. So there's a lot of different possible ways we can go with it, so we're going to give a flavor of that as we go through the examples today. So this is the conceptual framework that we're going to operate in today, and let's just see a bunch of different types of problems that come out of this. So one would be if we have a precipitation reaction, we could ask you to calculate the mass of precipitates. We talked about sort of at a theoretical level what a precipitation reaction is, how to balance the equations, how to predict what is going to precipitate using solubility rules. Now we can start doing some stoichiometry related to that. So let's say we mix together calcium chloride into an aqueous solution of silver nitrate. We want to know what is the identity and mass of the precipitate that forms. So the first part, which is identifying the precipitate, is what we've already done. So this will be a quick review of that. So we have to write the chemical equation and identify what forms and identify what would be the insoluble product. So we're saying that we're taking calcium chloride, CaCl2, calcium chloride as an aqueous solution and reacting with silver nitrate, AgNO3. And then we form two products. When we combine two ionic compounds, we just swap the cations and anions. So our calcium, which is our cation from the first reactant, is going to get combined with nitrate, which is the anion from the second. So we get calcium nitrate. Calcium is 2 plus, so it's going to be 2 nitrates in that formula. And then the other product, we're going to take silver, which is silver plus from our second reactant, combine it with the anion chloride from the first, and get silver chloride. And then we have to identify which of these would be our precipitate. So remember, anything that has nitrate in it is going to be soluble, so that's going to remain aqueous, dissolved in the solution. But silver chloride, most silver salts are going to be insoluble unless they're with nitrate or perchlorate or something like that. It's a couple of those special anions. So this is going to be our precipitate that forms. We'll abbreviate that with a little s to show that. And then to go along and balance this equation, we have 2 chlorines on the left from calcium chloride, so we need to put a 2 there. So we now have 2 silvers on the right, so we put a 2 there, and everything should be balanced at this stage with just a couple of coefficients. So that's the chemical equation. We also could, if we wanted to, write the net ionic equation. So we've identified what's going to precipitate, which is silver chloride. The net ionic equation will just be the 2 ions that are involved in forming that. All right, and in principle, when we're doing solution stoichiometry problems like this, we've identified what the precipitate is. That's the first step, and then the next step is going to be to calculate what mass of it forms, what mass of silver chloride do we get in this reaction. We could use either the full molecular equation or formula equation, or we could use the net ionic. And again, don't have a pointer because every time I restart this stupid tablet, it goes away. You guys are like, what is he pointing at? There we go. All right. All right, so we have this silver chloride as our product that's forming, and we have both the formula equation that we started with, or we can write the net ionic. In principle, we could use either one when we're doing solution stoichiometry. I think it's more convenient just to use the full equation. Because you have to sometimes do extra conversions with the net ionic that are a little bit source of confusion sometimes. So we'll just use the formula equation in general when we're doing these types of problems. All right. You should still know how to produce the net ionic equation, but for stoichiometry problems, there's no real advantage to using that. I think just the formula or molecular equation, as it's sometimes called, is perfectly fine, and there's no need to really go beyond that when you're setting up the equation. Okay? Because just like any other stoichiometry problem that we've been doing, you need to start with the balanced equation. You can't go anywhere without that. But I think the formula equation is the more convenient one to use in these situations. All right, so having identified the precipitate, the next step, as I said, is to calculate what mass of it will form. So we want to keep that balanced equation in mind as we do this. So we're going to make sure we keep track of that. And the coefficients especially are going to be important. All right, and so we're told here that we have excess calcium chloride, so that we don't have to worry about the exact amount of. This is going to be our limiting reagent, silver nitrate, and we're going to calculate then the mass of silver chloride that forms. So we can set this up as a string of conversions like we do for any other stoichiometry problem. We start with what we're looking for, which is the grams of silver chloride that's going to form, and we start with our given information. So we have 250 milliliters of solution, so that's the amount that we know to start with. And that's 250 milliliters of our silver nitrate solution. And then in this case, we're not starting with a mass of a substance, we're starting with a solution and a molarity. So we're going to use the molarity as a conversion to get moles of silver nitrate. So as I said many times when doing stoichiometry problems, your first step should always be to try to convert into moles, and that's how we're going to do it here, is using volume and molarity. So we have a molarity of 0.0555, so we want milliliters of the silver nitrate solution to cancel out, and we want moles in the numerator, so we're going to multiply by that molarity. 0.0555 over 1,000 milliliters. Our molarity is moles per liter, so it's going to be moles per 1,000 milliliters if we're doing it that way. So milliliters cancel out, and then we have moles of silver nitrate. And then from here, we can convert into moles of our product, which we're trying to find the mass of. So now we're just in the typical stoichiometry setup of going from moles of one substance into moles of another. We use mole ratios to do that. So we want AgNO3 in the bottom to cancel. And we want silver chloride in the top. So we look at the coefficients now. We have a 2 in front of silver chloride. We have a 2 in front of AgNO3. So that's a 2 to 2 mole ratio, so same number of moles of each. Moles of silver nitrate cancel out. That gives us 2 moles of silver chloride. And then the last step is to multiply by the molar mass of silver chloride. So that's going to be grams of silver chloride per 1 mole. I was cruel and didn't give that to you here, but we can use the atomic masses to figure out what the molar mass of silver chloride is, which is going to be the atomic mass of silver, which is 107.9, plus the atomic mass of chlorine, 35.45, both of those numbers from the periodic table. So it's going to be 143.4 grams per mole. So we're going to put that number up here to convert back into mass. So moles of silver chloride cancels. That gets us to grams, which is what we're looking for. So we stop there and we get 1.99 grams. All right. So most of these steps are the same as any other stoichiometry problem. We just started, instead of with a mass, we started with the volume of a solution, and a molarity was what we used to convert into moles in that first step. All right, questions on that? All right, let's just do one other example similar to this, but this time we have to deal with a limiting reactant situation. So now we have 125 milliliters of 0.25 molar sodium sulfide, and we're combining that with 95 milliliters of 0.45 molar lead nitrate. We want to know what mass of precipitate that forms. Again, we're not telling you what the precipitate is, so you have to identify that first by writing a balanced equation. So before we start worrying about the numbers, it's important to have a balanced equation in front of us. So we're going to take sodium sulfide as an aqueous solution. Lead nitrate is the other reactant. And we're going to form two products. We're going to take sodium and pair it with nitrate to form the first product. So that's going to be NaNO3. And then we're going to take lead Pb, which is 2 plus in this case, pair it with sulfide, which is 2 minus, and make PbS, lead sulfide. All right, we identify which ones are and are not soluble. So sodium nitrate has both sodium and nitrate in it, so it'll definitely be soluble. Lead sulfide, dead giveaway. If you see lead, that's likely going to be your precipitate, and it is here. It forms as solid lead sulfide. And then to put some coefficients in, we need a 2 there, a 2 there, and a 2 there, I believe. No. I screwed that up already. Alright, so we need a 2 there. That's it. Alright, so just 2 sodium nitrates that forms. We have one coefficient of 1 and everything else. Alright, so that's our balanced equation. Make sure we have the same number of ions on each side. Alright, so that's what we're going to form. So we're going to be looking now for the mass of that product that forms. Again, we're looking for the mass of the precipitate in this case, which is lead sulfide. This one's a little bit different, though, because we gave you the amounts of both solutions. So we know that we have 125 milliliters of 0.25 molar sodium sulfide as one solution, and we're mixing that with 95 milliliters of 0.45 molar lead nitrate, which is the other reactant. So just like any other stoichiometry problem, if we give you exact amounts of 2 or more reactants, you have to first figure out which one the limiting reactant is. And so we're going to follow the same steps for doing that we did before, which is to find the moles of each reactant and then determine what's called the stoichiometric ratio and identify the limiting reactant from there. So for each one of these, sodium sulfide and lead nitrate, we're going to determine moles first. But this time, as we did before, we have volume and molarity. So we have, for sodium sulfide, 125 milliliters of the aqueous solution. And we use the molarity, which is 0.250, to figure out number of moles. So that's going to be moles of sodium sulfide per 1,000 milliliters of the solution. So what we have is 0.0312 moles of sodium sulfide. Remember, the number of moles does not directly tell you what limiting reactant is. You have to divide that by the coefficient to get what is called R. In this case, the coefficient is 1, so it's the same number. Sorry, just 1, 0. So that's the stoichiometric ratio for sodium sulfide, 0.0312. And then we're going to do the same thing for the other reactant, which is lead nitrate. So whenever you have amounts for two reactants, you have to do this for both to figure out which one the limiting reactant is. Or this is, I suppose, one way to do the problem, but there's other variations that work well. In this case, we have 95.0 milliliters. So again, that's the given information in the problem. That's how much of the lead nitrate solution we have. Directly told us in there. So that's lead nitrate. And then the molarity of that solution is 0.45. So we're going to use a different molarity this time to convert into moles of lead nitrate. So that's 0.45 moles of lead nitrate per 1,000 milliliters of solution. And so what we get in this case is 0.0428 moles of lead nitrate, and then the stoichiometric ratio for that, again, there's a coefficient of 1, so it's the same number. Number of moles divided by the coefficient. There is no coefficient, meaning it's 1, and so we get a stoichiometric ratio of 0.0428. So which one of these is smaller is going to tell us what the limiting reactant is. That's this one here. So sodium sulfide is our limiting reactant. We've identified that as being limiting in this case. So then once we know what the limiting reactant is, just like any other stoichiometry problem, we use that amount of substance to calculate whatever it is we're asked to calculate in the problem, which in this case is mass of product. So starting with the limiting reactant then, we can calculate now in the last step, we just calculate the amount of product that forms. So the mass of lead sulfide that forms is going to be starting with our limiting reactant, and we don't have to necessarily redo this step here. We can start directly with moles of limiting reactant, which is 0.0312, that number we calculated earlier. So we have 0.0312 moles of our limiting reactant, which is sodium sulfide. And then going back to the balanced equation, we use mole ratios. So we need to find the ratio of moles of lead sulfide to moles of sodium sulfide. And going back to our equation, we see that there's coefficients of 1 for both of those. 1 lead sulfide, 1 sodium sulfide. So they're a 1-to-1 ratio, same number of moles of each involved. And then finally, we have moles of our product. We want to get grams of product, so we use its molar mass, which I gave you here, 239.3. So 239.3 grams. So this one sort of combines things from both what we did in Chapter 5 and the new stuff in Chapter 6. We're using volume and molarity to find moles of reactants, but then once we have moles of reactants, we're going to calculate grams of product, which is what we did before, same way we did in Chapter 5. So moles cancel out. That gives us to grams, and we get 7.47. All right, so again, the only new step here is using volume and molarity to find moles, which sort of adds to the toolbox that we have for determining moles of substances based on some, expanding on what we did in Chapter 5. All right, questions on this one or the one before it, this type of stoichiometry problem? All right, so what we're going to move on to next is called titration. And there's always collective groans and things when I say that word. It's really not that bad. And it's a fancy word, and you probably already have horror stories about it or preconceived notions about how bad it is. This is really just another variation on solution stoichiometry. So it's really just, again, using volumes and molarities as conversion factors to go into a number of moles, relating moles of substances to each other, and determining something about a substance that you're reacting. So really what's the definition of molarity is you have typically one solution that you have a known molarity or known concentration. So you're going to be, in a titration, you're going to be combining two solutions to each other. And one of those solutions has a known concentration. And you're going to use that solution to determine an unknown concentration of something else. Okay? So if you've ever done a titration in a lab, you have typically one of your solutions will be sort of in a beaker or a flask of some sort, and then the other one you use a burette to deliver a set volume of the other solution. And at least one of these two solutions, typically the one that you're measuring the volume of, you know the molarity of, although you don't necessarily have to be the case. But one of these two solutions, you know the molarity, and then you're going to use the titration data to figure out what the molarity is of the other one or some other property of that other solution. Okay? The most common type of titration that we'll deal with are acid-base titrations. So you're going to add a solution of a base to an acid or vice versa. So it works both ways. You can either add the base to the acid or the acid to the base. And again, the goal is typically to, one of those two solutions, the acid or the base, you don't know something about it. You either don't know what its concentration is, or you don't know its molar mass or something about it, and you're going to use the titration to figure that out. All right, and then when we do a titration, we add enough of the solution until we get to what's called the equivalence point. So in an acid-base titration, the equivalence point is defined as the point where the moles of OH minus or H plus that's added to this, that's added in the titration, all right. And so what that basically means is if you're adding a base to an acid, you have some number of moles of H plus in your acid, and you're going to add just enough base until you've reacted all the OH minus with the H plus. Remember, in an acid-base reaction, H plus and OH minus react with each other to make water. And so once you've added exactly enough OH minus to react with all the H plus, that's called your equivalence point, or it works the other way. If you're starting with a solution of a base down here and you're adding a solution of an acid through the burette, it's the equivalence point is the point where you've added just enough acid to react all the OH minus. Now the question is, how do you know when that happens? Because you can't really easily see H plus and OH minus, and you typically use what's called an indicator. This is the low-tech way of doing it. Is to use an indicator which changes colors at the end point. And we're not going to go into the details of the different types of indicators or how they work or anything like that. That's a topic more for the lab course. But an indicator changes color at the endpoint. So if you're adding a base to an acid, you put a little bit of indicator in with the acid. The indicator would be typically colorless in the presence of acid. And then once you've consumed all the acid, once all the H plus is gone by reacting with the base that you're adding, the indicator will change to a different color. The common one, which is called phenolphthalein, goes from colorless to pink. All right, so that's kind of the idea of a little bit of how we do titrations. The more important thing for this course is we're going to be doing calculations involving titration. So we're not going to be, this is not a lab course obviously, so we're not going to be doing them ourselves, but we're going to be using fictitious data from titrations to do different types of problems that we'll see. All right? So that's kind of the basis of a titration, and then a lot of different problems then that can come out of this. So one thing we could ask is, this is not really how you typically use titrations, but let's say we know the molarity of both solutions. Let's say we have 0.126 molar sodium hydroxide solution, and we're going to add that to 52.3 milliliters of 0.297 molar H2SO4. All right. And I still remember this. It was a pretty vivid memory. There's a test question from when I was taking General Chemistry 1 when I was, way back when I was your age, where it was, I don't know if it was sulfuric acid, but basically you know that sulfuric acid is really bad to drink, right? So you wouldn't want to drink that stuff. It would erode you from the inside. And it said, let's say that you were in a hostage situation, and the person that's keeping you hostage was going to force you to drink this much sulfuric acid. How much hydroxide would you have to add to that to neutralize the solution and save yourself? So imagine this as a life or death situation. We have to figure out, Because if you add too much sodium hydroxide, the solution is going to be basic, and that also does bad things to your body as well. So you have to add just enough of your sodium hydroxide solution to completely react all the acid, and then you'll be safe, and you can drink that, and it's basically like salt water at that point. Okay, so imagine this is that harrowing of a situation. We have to figure out how to do this. So just like any sort of stoichiometry problem, for titrations, we're going to start with a balanced chemical equation. And typically what we really care about in a titration are the two reactants, because we're measuring the amounts of two things that we're reacting with each other as and really it's those two that we're going to be dealing with. We want to be aware of what the products are, but the products don't usually matter for a titration problem. It's just the two reactants and especially their mole ratio. So the balanced equation for this, most of the titration problems we're going to do are acid-base reactions, so we have to remind ourselves of what those look like. So we're going to take sodium hydroxide, which is NaOH, that's going to be our base. Combine that with H2SO4 sulfuric acid, which is our acid. And then the two products, again, are going to be a salt and water. So the cation from the base and the anion from the acid combined to make, in this case, sodium sulfate. And then you would make water, which is H2O. So again, the second product in the acid-base reaction is always the H plus and OH minus. What we really care about in titration problems or any sort of stoichiometry problems involving acids and bases like this, what we really care about is the ratio of the two reactants. And the simple way to do that is to look at the number of OH minuses, the number of H pluses. As we talked about, those need to be equal to each other in the balanced equation. So our base has one OH minus, but our acid has two H pluses. So that means we have to put a coefficient of 2 here to ensure that we have equal numbers of OH minus and H plus reacting. That will also give us a coefficient of 2 in front of water. We don't need a coefficient in front of sodium sulfate, but like I said, the products are not terribly important for this and for just about every sort of titration problem. So then the question asks us, we can go into then doing the calculation. We want to know how many milliliters of our sodium hydroxide solution is needed. So we're looking for milliliters of solution. That's what our ending point is going to be. And if we so desire, we can set this up as just a long string of conversions. So we start with what we know. When we're doing a titration problem, we're typically going to start with the solution where we know both the volume and the molarity. So in almost every situation, at least one of the two solutions, you're going to know both volume and molarity, and that's going to be what your starting point is. So we know that we have 52.3 milliliters of sulfuric acid, and we know that its molarity is 0.297 molar, so that's going to be our starting point. Because if we know volume and molarity, as we've already talked about today, we can find number of moles. So we have 52.3 milliliters of our H2SO4 solution, and our first step is going to be convert to moles, and we're going to use the molarity to do that. We can't do that for sodium hydroxide because we don't know the volume that we're adding. That's what we're trying to find out. So if we know volume and molarity, that's what we're going to start with to find moles. So sulfuric acid is 0.297 moles. So that's what that capital M tells us, moles per 1,000 milliliters. We'll use that shortcut again. So that's moles of sulfuric acid. Our next step is to find how many moles of sodium hydroxide we had to use to react with that. All right, so we added enough of this sodium hydroxide solution to completely react with our H2SO4, and so we're going to now use mole ratios between the two to figure out how much sodium hydroxide that corresponds to. Okay? So if we go in here, we see that our coefficient for sodium hydroxide is 2, so it's going to be 2 moles of NaOH on the top and a coefficient of 1 for H2SO4, so 1 mole H2SO4 on the bottom. That means for every 1 mole of sulfuric acid that we had, we needed to add 2 moles of sodium hydroxide. Moles of H2SO4 cancel. Now we have moles of sodium hydroxide. What we're trying to find, though, is how many milliliters there are. So what's the relationship between milliliters and number of moles? All right, molarity, I think I heard it. So we're now going to use the known molarity of our sodium hydroxide to convert into milliliters. So this time we're going to do it opposite. We want milliliters in the top, and we want moles of NaOH to cancel out. And so we're actually, in this case, going to divide by the molarity. So the molarity is 0.126, which means we have 0.126 moles of NaOH per 1,000 milliliters, or per 1 liter if you want to do it in 2 steps. And now moles of NaOH cancel out, and that gets us into milliliters, which is what we're looking for. So this time we use that molarity in sort of the opposite direction. We divided by it to go from number of moles back into volume, which is what we had to do here. All right, you could do this stepwise. You could have found number of moles first and then set up a ratio with molarity and all that stuff. But here we did it in just one fell swoop, and what we get is, if I did this correctly, 247 milliliters of our NaOH solution. All right, so you would have to add 247 milliliters of sodium hydroxide solution with this molarity here to be able to completely neutralize this acid, to completely react all of the H2SO4 that's in there. All right, questions? Okay. And we're just going to keep doing a bunch of these now to see all the different variations we can have for titrations. So we're going to just plow right through a bunch of these. All right, another thing that we can do with titrations, and probably the more typical use of a titration experiment in a lab, is to determine an unknown concentration. Okay? So one way to do that is, the way we commonly do it in the lab is use an acid called KHP, which is nice and convenient. We can weigh it out as a solid. So we have KHP is an acid with one acidic proton, and it's commonly used to standardize NaOH solutions. So standardize means to determine the concentration of or molarity of. So if you have 1.25 grams of KHP and you dissolve it in water, and we add 56.3 milliliters of NaOH to reach the endpoint, what is the concentration of the NaOH solution? All right, so in this case, we're not directly calculating an amount of substance. We're actually calculating a molarity of that solution, or a concentration, which would typically always be in units of molarity. All right, so the first thing to think about is the balanced equation. We can't really do it in full detail here because we don't have the exact formula or structure for KHP, but we have KHP, which is our acid, sodium hydroxide, which is our base, and what we're told in the problem is that KHP is an acid with one acidic proton, so that means it has one H plus associated with it. We know that sodium hydroxide, as we saw in the last problem, has one OH minus, so that means that these two will react in a 1-to-1 ratio. Because there's one H plus from our acid, one OH minus from our base, so those will react with each other 1-to-1. Okay? So you have a 1-to-1 ratio of those two. The other two products we don't really care about for a titration. It's going to be some sort of a salt, KHP minus, whatever that is, and water. But like I said, for titrations, we don't even need to know what the products are or what their ratios are. All we really need to know is the ratio of the two things that are reacting with each other, usually an acid and a base. All right, so we know that these two things react in a 1-to-1 ratio. It's also helpful to think at the beginning of the problem of what exactly are we looking for here. So in this case, we're looking for the molarity of the NaOH solution, so it helps ourselves to remind ourselves of what the definition of that is and what two things we need to find that. So remember, molarity is moles per liter. So we need the number of moles of NaOH, and we need the liters of that solution. Okay? If we look at the problem and the information in the problem, typically one of these two is given to us, and it's going to usually be the volume. So we know that we're using 56.3 milliliters of NaOH. That's how much we had to add to reach the endpoint. So we have the volume given to us. It's in the wrong units, but it is given to us as milliliters. We just have to convert that to liters. So we already have volume of solution. What we need to find now is the number of moles of NaOH, and that's what we're going to use the titration data to do in this type of problem. Okay? So we're going to look for moles of NaOH. And we know in this problem that we're starting with our acid KHP, we have the mass of our acid, and we have its molar mass. We can figure out moles of KHP. So we have 1.2. That's not the formula, by the way. It's not potassium, hydrogen, phosphorus. That's just an abbreviation, in case there's any confusion there. I should have mentioned that, but not important. So we have KHP, which has a mass of 1.25 grams, and we know the molar mass of KHP, which is given to us, is 204, so we can calculate moles of KHP by using the molar mass, just like we do all the time in stoichiometry. So 1 mole has a mass of 204.22. That's given to us in the problem as well. That's the molar mass given here. So that's moles of our acid. Now we can find the moles of NaOH, which is what we need for this calculation up here. And those react in a 1-to-1 ratio, so it's just 1 mole of NaOH for every 1 mole of acid that we started with. Okay? And again, that's because the coefficients in the balanced equation are both 1, so they react in a 1-to-1 ratio. Usually for acid-base problems, they're pretty simple mole ratios, 1-to-1, 2-to-1, maybe like 3-to-2 at the worst. So we have 1 mole of NaOH for every 1 mole of KHP, and we stop there and calculate that we have 0.00612 moles of NaOH. Did I give us another page to do this? I did, good. All right, so that's moles of NaOH. And then the other piece that we need is liters of solution. We didn't give that to you directly, but we have milliliters. So the liters of our NaOH solution that we added is going to be 56.3 milliliters. That's the amount we added to reach the endpoint. And then 1 liter over 1,000 milliliters. All right, so we added 0.0563 liters of our solution. So that's the volume that we're going to use to calculate molarity. All right, so we have moles, we have liters, and now we just need to divide the two to find molarity. Okay? So the molarity of our NaOH solution is the last step, is going to be the moles that we calculated from the titration data, 612, 00612, sorry. All right, so that number we got from the titration. The volume of solution, which was a measured quantity that was given to us, we had to convert into liters though. And when we divide moles by liters, what do we get? 0.109. All right, so that's the molarity, the concentration of our NaOH solution. All right, so that's how we use titrations to figure out unknown concentrations. So you again look at the problem, what it's asking for. If it's asking for a concentration or a molarity, we need moles of that solute. We need moles of that solute. We need liters of the solution, and we divide the two to get molarity. All right, questions on that one? All right. Something else that we can do is determining. Here's another example of determining an unknown concentration. So this is just a rehash of that. So one other example that's very similar, in this case though we're mixing two solutions instead of a solution with a solid. So here we have an unknown acetic acid solution, and we have 100 milliliters of this solution added to a flask, and we titrate with 0.125 molar NaOH. This time we know the concentration of the base. We add 53.24 milliliters to get to the endpoint. We want to know what is the concentration of acetic acid. Okay, so in this case we didn't give you any masses or molar masses. Everything is dealing with volumes and molarities. So it's helpful to think about what we're looking for, which is the molarity of acetic acid. CH3COOH is the formula for that. And that's going to be the moles of the acid, CH3COOH, acetic acid, per liter of solution. So just like before, we need molarity, and we need to find molarity, we need the moles and we need the liters. Okay? All right, we were told in the problem that we have 100 milliliters of our unknown solution, our solution with unknown concentration. So that's the volume of our acetic acid, which is 100 milliliters, and we just divide that by 1,000, get 0.1 liter. That we can do in our head, I think. So we already have the volume, 0.100 liters, and we just need to find the number of moles, put it up here, and divide to get molarity. All right, so once again, it's helpful to think about the balanced equation. So we have CH3COOH is our acid, reacting with the base, which is still NaOH. All right, maybe not obvious from the formula, but acetic acid has one acidic proton. Only the hydrogen that's bonded to oxygen is acidic. The other three hydrogens don't react with bases. So we get a one-to-one reaction again, 1H plus, 1OH minus. The products, which we don't really care about, if we want to be complete, are going to be sodium acetate and water. Okay? But the important part is to know that the acid and the base, again, react in a one-to-one ratio. Acetic acid has 1H plus, sodium hydroxide has 1OH minus, so it's once again a one-to-one ratio of the two. And then just like in the last problem, we're going to find moles of our acid, which we don't know, by using the titration data, the amount of base and its molarity that we added. Okay, so we added 53.24 milliliters of our NaOH solution. So if we start with the solution where we know the volume and the molarity, we know that we added this much NaOH in terms of milliliters. We know the molarity is 0.125, so we can use those two numbers to find moles of NaOH that we added. So 0.125 moles of NaOH per 1,000 milliliters. Again, that's just the molarity of the solution that we're given. And then from the balanced chemical equation, we have 1 mole of acetic acid for every 1 mole of NaOH, because they react in a 1-to-1 ratio. So we end up with 0. This is an unlucky number, but this is just how the math worked out. 0.00666. Sorry, if you're superstitious, I apologize. Moles of acetic acid. I should fix that in future iterations of the course, so people don't get the wrong idea about me. Or anyway, so the although you may already think that anyway. 0.00666 moles of acetic acid. That's the volume that we determined. So we divide the two to get the molarity, which is still an unlucky number, but one less decimal place. 0.666 molar. Okay. So same steps as the last problem, just a little bit different because here we didn't have the mass of our known substance and its molar mass. We instead had a volume and a molarity. So once we know the volume and molarity of one of the solutions, we can find moles of that solute, NaOH. We relate the moles of our unknown using stoichiometry, the mole ratios, and then we divide that by the volume. So typical type of titration problem here where we're finding an unknown concentration. Okay, questions on that one? All right, the other way we can do titration, so there's all kinds of things we can do with this. It's a lot of fun. There's so much variety here. Is we can find an unknown molar mass. This is actually a technique that people use sometimes, where if you have an acid, but you don't know the molar mass of that acid, you can use a titration to figure out what it is. Okay. So here we have 0.254 grams of an unknown amino acid, which we'll abbreviate with HX, meaning it has 1 acidic proton, and it's dissolved in water. We titrate with that same 0.125 molar solution, and we require, in this case, 27.1 milliliters to reach the equivalence point or the end point. What is the molar mass of the unknown acid? So we've done some problems recently in Chapter 5 that required us to determine unknown molar masses. In those cases, a lot of them were unknown atomic masses, where we had to identify the element using its atomic mass. So anytime we're looking for an unknown molar mass, in this case of our amino acids abbreviated HX, remember the two things that we need. The definition of molar mass is the grams of that substance per mole. So we need the grams of our unknown acid, which is given to us, and we need the number of moles of our unknown acid. Okay? So this numerator here is given in the problem. We know that we're starting with 0.254 grams, if we don't know the moles yet. So we have 0.254 grams of our unknown acid, and this we're going to find using the titration data. Okay? So a very common theme that's emerging in titration problems is you're going to use the information in the problem to find moles of substance, and then you're going to do different things with that quantity once you have it. So we can use the moles of substance to find molarity like we did in the last two. In this case, we're going to use moles of substance as part of a calculation of molar mass. So it's again helpful to think about the balanced equation, which for most acid-base problems is pretty simple. So it's going to be HX, the abbreviation H with just a single hydrogen tells us there's 1 acidic proton, still NaOH, so those are going to react in a 1-to-1 ratio once again. We would form a salt and water, but we don't really care about the products for these. But again, the important part is that they react in a 1-to-1 ratio whenever you have 1 acidic proton and a base that has just 1 OH minus. So we're going to use the information in the problem then to find the moles of our unknown acid HX, because we have the volume of our base, 27.1 milliliters that we added, and we also have its molarity, which is still 1.125 molar. Okay, so we start with the known volume and molarity. So 27.1 milliliters of our NaOH solution was added. Its molarity is given as 0.125 once again, so we're going to use that to find moles of NaOH. So that's 0.125 moles per 1,000 milliliters if we do that in one step. And then we use mole ratios to figure out how many moles of acid there are. It is again in this problem 1-to-1. It won't always be 1-to-1, so you have to make sure you have the balanced equation and look at the coefficients. Don't just assume that this will always be 1-to-1. But it's 1-to-1 here because both acid and base have coefficients of 1 in front of them. And that allows us to calculate that we have 0.00339 moles of our acid HX. So now that we have the grams, which is given, and the moles, which we just calculated, we can find the molar mass by dividing the two. All right, so we use the mass, which is 0.254, given to us in the problem. You need to know at least one of these two quantities to get the molar mass. So we have 0.254 grams, which we would have weighed out at the beginning of the experiment. We calculated from the titration that there's 0.339 moles of acid. And what we end up with is 74.9 grams per mole. Okay? So anytime you have mass and number of moles, you can divide the two to find molar mass for an unknown. All right, questions? All right, so again, just more variations on the same theme, using titrations to find moles. All right, last one that I think we'll do, yes, is a redox titration. So as I said, we're going to mostly talk about acid-base titrations, but you can also do titrations for redox reactions that we just talked about Monday. And a common one that you would use would be to determine, let's say, the concentration of hydrogen peroxide in something. So the active ingredient in hair bleach is hydrogen peroxide. So I got my hair cut last weekend, but I opted not to get frosted tips. I didn't use this stuff. But if you wanted to, you would use some sort of hair bleach that has hydrogen peroxide usually. And we want to determine what's the mass percent. So we have 14.8 grams of that hair bleach solution, and we titrate it with KMnO4 solution. So MnO4 minus being the reactive anion, the piece that's important, potassium just being a spectator. If we use 43.2 milliliters of that solution to reach the endpoint, what is the mass percent of H2O2? So we can, again, use titrations to figure out some unknown concentration or unknown quantity. It turns out, you might be wondering, well, how do we do these titrations? What's the indicator? Blah blah blah. We don't actually need an indicator for this because KMnO4 minus is very bright pink. MnO4 minus by itself is bright pink. And manganese 2 plus is nearly colorless. So basically, as you add the MnO4 minus, it'll react with H2O2 and convert to something colorless. And then once you've added just enough of that, the solution will stay pink because this won't have anything left to react with. So this is what's called a self-indicating reaction. Just a little piece of trivia that you probably don't care about, but we don't need an indicator here because one of our reactants has a very distinct color to it. But we're going to again do the same thing. We have to figure out what we're looking for, which is mass percent of hydrogen peroxide. And we haven't dealt with mass percents of solutions too much, but this is another concentration unit, and we kind of already know the definition of mass percent in other contexts. So mass percent of a solution is going to be the grams of the solute, which is H2O2, divided by the grams of the solution, which in this case is our hair bleach, multiplied by 100. Okay, so that's sort of the definition of mass percent for a solution, which we've seen a couple other times in example problems. But mass percent of a solution is mass of solute divided by mass of solution times 100. So defined very similarly as other mass percents that we've dealt with. All right, so in this problem, we know that we're analyzing 14.8 grams of the solution, so that's going to be our denominator. But what we have to figure out is how much H2O2 is in there, and we're going to use the titration to tell us that. Okay? So believe it or not, we have enough information to get that. It's going to be a lot of steps, as we'll see, but once again, we have one solution, our MnO4 minus solution, where we know the volume of that solution and we know the molarity. So if we know volume and molarity, we can find moles of this reactant, and we can use stoichiometry to find the moles of H2O4 and then go to grams from there. So it's a lot of steps, as we'll see, but they're all steps that we should be familiar with now. So we're looking for the mass of hydrogen peroxide. So we start with a solution where we know the volume and the molarity, so that's going to be KMnO4. That's what we're titrating with, our titrant. The molarity of that solution is 0.105, so we have 0.105 moles of KMnO4 divided by 1,000 milliliters of that solution. So that's moles of KMnO4. Now, if you're looking at this closely, you'll realize that the chemical equation we're given doesn't have KMnO4 in it. It actually has MnO4 minus. This next step is a trivial one, and one you might just be able to recognize by inspection. But technically speaking, we need to find moles of MnO4 minus because that's what's in our balanced equation. if we look at the formula of KMnO4, KMnO4 has 1 potassium and 1 MnO4 minus. So for every mole of KMnO4, we have 1 mole of MnO4 minus anion. So this is a trivial step that you don't necessarily have to do explicitly, but we should recognize that we're actually looking for just the anion permanganate in this case. Sorry, I left the word out. There should be moles there too. All right, so now we have moles of MnO4 minus. We want to figure out how much hydrogen peroxide is in their H2O2, and so we're going to use mole ratios now. So once we have moles of one reactant, we can find moles of another reactant using mole ratios. This time it's a little bit more complex because it's going to be 5:2. So moles of H2O2 on the top, moles of MnO4 minus on the bottom from the chemical equation. We see that MnO4 minus has a coefficient of 2, H2O2 has a coefficient of 5. So now we have moles of hydrogen peroxide, and once we have moles of a substance, how do we find mass? Our old friend, our old favorite. Moles to mass, we're going to use molar mass. So we're told here that the molar mass of H2O2 is 34.2, so we multiply that, 34.02 grams of H2O2 divided by 1 mole of H2O2, per 1 mole of H2O2. Okay? So moles cancel out, that gives us grams of H2O2, which is what we're looking for, so we stop there and find that we have in the solution 0.386 grams. So then to find mass percent, we take this mass, which is the mass of our solute, 0.386 grams, divided by the mass of our solution, multiply by 100 to get a percent, and we get 2.61%. So a little over 2.5% of the mass of our hair bleach solution is made up of hydrogen peroxide. The rest would be whatever else you need in there to effectively bleach hair, because I don't know what that is. All right, but the hair bleach is really, the H2O2 is the active ingredient. All right, any questions on that one? So that's a little bit perhaps more advanced, a little bit different variation of what we normally do, but it's just the same concepts of using titrations to find moles of substance and then relating that moles to something else. All right, that takes us to the end of Chapter 6, the end of Exam 2 material. So, yeah, but we can. That's what I was going to stop for, so go ahead.
So for the 0.105 mole on the
yes.
In the question, it's the 0.105 capital M. Is that the same thing?
So that's moles per 1,000 milliliters, or moles per liter. So this whole thing here, this whole conversion factor, as soon as my tablet lets me write again, it's just maybe the pen. All right. This whole conversion factor here came from that 0.105 capital M. So capital M means moles per liter or moles per 1,000 milliliters. So we use that as a conversion factor in this case to convert volume into number of moles. All right. So this, just to make sure don't forget to write it, this is the end of Exam 2 material on this slide. So everything else we do after this won't be covered in Exam 2. We have our usual exodus when I announce that. That's okay. And does anybody have any last questions on solution stoichiometry or any of these topics before I move on to the new stuff? Yes? This ratio is just from the formula of the compound. So it's just a slight technicality because we're telling you that we're adding in a solution of KMnO4, but our balanced equation just has the anion MnO4 minus. So we have to recognize that there's 1 mole of anion per mole of compound because the formula is KMnO4. If it was let's say if it was calcium permanganate, calcium MnO4 2, we'd have to recognize that there are 2 moles of anion per mole of compound. It's a trivial extension in this case, or a trivial step in this case, but sometimes if the reaction is written in ionic form with just individual cations and anions, you have to look at the compound that those cations and anions came from and figure out how many moles of that are in the compound you started with. So that's just it doesn't come up all the time, but if you're dealing with ionic equations, sometimes that's a factor you have to think about. All right, other questions on this? Yeah. How do I know if it's aqueous or solid? Well, here it's given to us. So the way you typically know, or the ones that we expect you know, would be based on solubility rules. So if we give you especially in a precipitation reaction setup, you should be able to predict which species are aqueous, those are the soluble ones, or solid, which are the insoluble ones. The other ones, like solid, liquid, gas, sometimes are not as obvious. In ionic equations, you typically assume that all the ions are aqueous, and then the other, neutral compounds that form are, it depends on what the substance is. The only ones we really expect you to predict are ionic compounds, whether they're soluble or insoluble. Okay? Yeah.
What purpose did all this was a Redox reaction serve for us?
It didn't really serve any purpose except just for your information. So no, I'm being serious though. That's not a snarky answer. So for titrations, acid base is the most common, but really any two solutions that react with each other, you could in principle do a titration with, and the math and the steps that you do are the same regardless of whether it's acid base or any other type. The only difference is that for acid-base reactions, you should be able to write the balanced equation. We won't usually give that to you. You'll have to know, that the two are reacting with each other and figure out if it's a 1-to-1 or 2-to-1 or whatever ratio. For redox reactions, you should know how to balance them, but if we use one in a problem, we would typically just give it to you because there's no easy way to predict that this is the outcome of this reaction. That, if you mix MnO4 minus and H2O2, that you get these products, there's no easy way to predict that. So we would just give you the full equation in that case. But once you have the equation, the series of steps is basically identical. Anything else? All right, all good questions. We have a lot more time for that on Friday if you have any lingering questions. But let's move on to the beginning parts of Chapter 7, which is a new topic. There will be some relationships to stoichiometry later on. But what we're talking about in Chapter 7 is energy. So, the primary context we'll deal with it in a chemistry sense is when we do chemical reactions. We talked a little bit about change in energy for chemical reactions already in Chapter 2. You have your reactants have a certain bond strength associated with them. Your products have different bond strengths. And so it's very often when you run a chemical reaction, you're going to either add or release energy from the system to allow that reaction to take place. We're going to start, though, with a very physics definition of energy and work our way into the chemistry aspects of it. So let's give the basic definitions first. So energy is defined as the capacity to do work. So work being essentially the ability to transfer that energy to something else and cause some sort of change in the two systems. But at this point, we just need to know that the definition of energy, there's two types of energy. It's going to be kinetic energy and potential energy. So kinetic energy is energy due to motion. So anything that's in motion has kinetic energy. You might know the formula is 1/2 mv squared, although we're not going to really use that in this course, but if you've taken physics, you've seen that. Kinetic energy is energy due to motion, and the potential energy is energy due to its position or composition. Now, when we're talking about chemical reactions, which we will eventually be dealing with exclusively in this topic, this chapter, there is kinetic energy present because we should recognize that atoms and molecules are always in motion, especially if we're dealing with reactions in solutions or in the gas phase. There's a lot of motion involved, but the kinetic energy in a chemical context is basically dependent on temperature. We'll get some more information about that later. So for a chemical reaction, as long as we keep the temperature constant throughout the reaction, we basically assume that the kinetic energy stays constant as well. So the type of energy that we're most concerned with from chemistry standpoint is potential energy, because the bond strength, which is basically the energy of attraction between protons and electrons that we've been talking about throughout this course, that is a form of potential energy. So when you have positive charges and negative charges attracted to each other, like we always do in chemical substances that are forming bonds between atoms, that is a form of potential energy, and that potential energy will very often change during the chemical reaction as we go from reactants to products. So potential energy is the one that we're going to deal with most in this course. And when we're defining energy, we have two frames of reference to consider. We have system and surroundings. So system is the part of the universe that we're studying, which we sort of define. So it's the part of the universe that we are focusing on. when measuring changes in energy. Because in most cases, we don't measure how much energy something has. We measure energy that is transferred, energy that changes throughout some process. So again, to sort of orient ourselves in the chemistry aspects of things, because we're going to start out very physics in this chapter, the system is usually the chemical reaction that we're studying is a closed container where a chemical reaction is occurring. We'll talk a little bit about physical changes, energy changes involved in physical processes where we're not actually doing a reaction, but we're just studying some physical change. So that we're going to see a little bit, so it doesn't necessarily have to be a chemical reaction. But it's usually a closed container of a substance and very often a chemical reaction that we're studying. All right, and then so you have your system, which is the little piece of the universe that you're focusing on, and the surroundings is everything else that's not part of the system. So the system is obviously quite large if it represents the whole rest of the universe. So typically when we're doing experiments, we're trying to measure changes in energy. So what's happening is that, as we'll see, energy gets transferred from the system to the surroundings or vice versa. It's always moving between the two. That's what we're always going to be studying. If the surroundings is the whole universe, that's kind of a cumbersome thing to study. So we play some tricks to really confine the surroundings to a much smaller, more manageable area. We're going to talk about that later on in this chapter. But the key concept here is that whenever we have energy changes, we're going to be transferring energy between the system and the surroundings, and we're going to be doing some measurements and calculations to quantify that. So when you have energy transfer between system and the surroundings, you can measure then the change in energy for the system, which is going to be the final minus initial. So anytime you see delta, we've seen delta capital letters a few times already. Anytime you see delta, that means final minus initial. So the change in energy for your system is the final amount of energy that it has minus the initial. And that energy is going to always be transferred between system and surroundings, and it's going to be transferred in two different forms, either heat and work. Okay? So whenever you're transferring energy, the only two ways that you can transfer energy are via heat or via work between the system and the surroundings. So either transferring heat from the system to the surroundings, or from the surroundings to the system, or transferring work from the system to the surroundings, or from the system to the surroundings, if I said that right. But it's always transfer between the two in the form of heat or work. So to define these two, heat is sometimes referred to as thermal energy, so also known as thermal energy. And this is energy that is transferred due to a temperature difference. And this is the one that we're going to be talking about a lot in this chapter. Especially towards the second half that we're going to get to next week. All right, so it's thermal energy, which is a result of a temperature difference between system and surroundings. All right, and this we should be familiar with in our everyday lives. Like if I were to take an ice cube and set it on this front table here, we know that eventually the ice cube would warm up and melt because there's heat being transferred. Anytime you have two objects in contact with each other that have different temperatures, there's going to be heat transfer between them until the temperature of those two ends up being the same. Or if you take a boiling pot of water and put it up here, eventually it's going to cool down until it gets to room temperature. So there will be heat transfer from the hot object to the cooler object, whatever's in contact with each other, until the temperatures of the two are equal. And that's what we call heat, which is one form of energy transfer. And then work has a pretty generic definition, but it's all other forms of energy transfer is work. We don't use this as much in chemistry. We don't usually think about the work that's being done in chemistry. This is more of a physics concept, although we'll see a little bit of it in here. So it's all other forms of energy transfer. And this is typically when an object is being moved by a force. So work is typically involving movement, where the system or the surroundings is applying a force on something else and causing it to move. That's what we typically think of as work. All right, so clearly that doesn't occur as often in a chemistry context because we're not really thinking about how we physically move things very often in chemistry. The form of energy transfer that's more common for us is heat, but we do want to know a little bit about both of them. So when you have a change in energy, when you have energy flowing between the systems and the surroundings, our change in energy delta E is given by the sum of heat and work. So as I said, it's always going to be some combination of heat and work that are involved in energy transfer. And if you know the heat and the work, you can calculate the change in energy delta E. So heat is abbreviated as Q, work is abbreviated as W, a little bit more obvious. And so the sum of those two, the heat, the amount of heat that's transferred plus the amount of work that's done or transferred, is going to be the change in energy delta E. And it's important for us to be familiar with the sign convention. So we're going to learn how to calculate Q and W in certain situations. But for now, let's just familiarize ourselves with whether they're positive or negative. Because delta E can be either positive or negative. Positive meaning that the system is gaining energy and going to higher energy. Negative meaning that it's losing energy, going to lower energy, just like we saw for chemical reactions that we talked about in Chapter 3 with bond energies. So the sign convention for heat and work, if we have a positive heat term, a positive Q, that means heat is absorbed by the system. Okay? Or it also means that the system is getting warmer. It's taking heat from the surroundings and getting warmer. So anytime that happens, the Q will be positive. We're going to learn how to calculate the actual value of Q later. That's the sign that we're going to see. And then if we have a positive work term, that would mean that work is done on the system. So our reference point in this is always the system. So we're measuring delta E for the system. And so if W is positive, that means that work is done on the system. Okay? And if Q and W are both positive, that must mean delta E is positive, right? If you add two positive numbers together, you get a positive number. That's relatively basic math, I think. So anytime that's the case, where you have both positive Q and positive W, you're going to have a positive change in internal energy. Your internal energy will increase for your system. All right? Now we also can have, though, negative Q and negative W. So let's say we have, well, let's do the easy one first. So if we have, the other convention is that for negative Q, that means heat is released from the system. So negative Q means that heat goes from the system to the surroundings and the system gets lower in temperature. So that's what we mean by negative Q. And then negative W would mean that work is done by the system. So if the system is doing work on the surroundings, it's going to be losing energy and have a negative contribution for W. And if you have both of those negative, of course, the delta E will also be negative, and that means the internal energy has to decrease. But of course, it is also possible to have a combination of plus and minus. So you can have positive heat, negative work, or vice versa. So if we have positive heat term, meaning that heat is absorbed, but at the same time, our system is doing work, which gives us a negative W. If we have a positive and negative, whether delta E is positive or negative depends on the magnitude of Q and W. All right, so if Q is larger than W, it'll be positive. If Q is smaller, it'll be negative. So if one of them positive, one is negative, the delta E is, again, the sum of the two, and it could be positive or negative. And then last possible combination would be if you have heat released by your system, which is negative Q, but at the same time you're having work done on the system, so you have a positive W. Again, delta E could be positive or negative depending on the relative magnitudes of Q and W. All right, so it depends on the magnitudes of Q and W, whether that's positive. So these are the sign conventions for heat and work. And then the last thing that I want to cover today then is what's called path independence, or the definition of a state function. So for our purposes, a state function is anything that has delta in front of it. It's called a state function. So delta E would be an example of a state function. So anything that can be written as a delta type function is called a state function. And the idea of a state function is that so delta E or any state function really depends only on the initial and final states, not the path that we take to get there. And so that's what we mean when we say that something is path independent. It depends only on the final and initial states and not how we get there. All right. So in this example that I have down here, let's say we know that our initial state, we don't normally know the actual energies of our initial and final states, but let's say we did in this case. If our initial state has an energy of 10 joules and our final state has an energy of 20 joules, our delta E is just given by the difference between those. Final minus initial, which is plus 10 joules, okay? So if we know the final and initial state, that's all we need to find delta E. And it also means that it's path independent. It doesn't matter how we get from the initial to the final state. So there are infinite numbers of ways that we can get from here to here and still get a delta E of plus 10. It doesn't matter how exactly we do that. So as one example, let's say we have our initial state, and let's do 30 joules of work on it. So that 30 joules of work is going to take us to a state that has an energy of 40 joules, so we've just added 10 joules to 30. But then let's say at the same time or subsequent to that, we're releasing or losing 20 joules of heat. So for this process, delta E is equal to Q plus W, which is also plus 10 joules. W is 30, Q is minus 20, the sum of the two is still plus 10. So this is one path we could take to get between our initial and final states, but we could also do it a different way. Let's say we first did minus 20 joules of heat was lost from the system. That takes us to a state where the relative energy is negative 10. But then let's say after that we did 30 joules of work to get us back up to here. So then delta E is still Q plus W, which is still plus 10 joules. So this little illustration here, which is just picking two random paths, tells us that delta E, which is a state function, is path independent. There are infinite numbers of ways to get between the initial and final state, different combinations of Q and W, or just Q by itself, or W by itself, infinite combinations of Q and W that will result in a delta E of plus 10 joules. All that really matters is what are the initial and final state. That's all that we need to determine delta E. So that will, we're going to introduce one other state function next time that's a little bit more convenient than delta E, and get into some examples of how you measure that in an experimental setting. All right, but last reminder, exam review Friday. If I don't see you there, I'll see you in class next Monday.